All right, team. Let's talk about electrostatic forces and electric fields. Specifically, let's talk about electric fields. Because I want to get you ready for the next APR. And, no, not the next APR, the next T. And also get you ready for the quiz. So let's jump on it really fast. So let's write down electric fields. We've done studies thus far of two charged particles or more, and what forces are being experienced between the two charged particles, Q1 and Q2. Okay, but that is the extent of our knowledge between the differences or the mixes between two charged particles or more charged particles. We understand that the electrostatic force is equal to the Coulomb's constant times charge 1 times charge 2 over r squared, which is the distance between charge 1 and charge 2, r. And these are absolute values. Okay, because what matters is you understanding whether the forces are repelling or attracting, and all in terms of your coordinate axis. But now we are going to study what's happening between just one charged particle. And let's bring charged particle 1 down here and put it as charged particle 1. And let's say that this charged particle is positive. Even though it doesn't have a force or another particle approaching it or affecting it, creating the force, this charged particle does experience electric field surrounding the charged particle. And because it's positive, this charged particle has electric field lines that are coming out of the charged particle. Okay? So all of these are electric field lines. All of them are electric field lines. And what this does is that these are not forces per se. But let's say that a charged particle, a positive charged particle, comes into the spectrum of this other charged particle of charge 1. And I don't know how this happened. Here we go, delete. And let's highlight this. And this charged particle starts moving. All of a sudden, it gets to here. And at this moment, we can analyze, because we understand the electric field that's going on at this position right here, we can analyze what is the force being experienced by this charged particle here due to the electric field that I just highlighted. And this charged particle, because both of them are positive and positive, has a force that is being repelled, a force that is being repelled, and we can go about and analyze, actually get the equation. Force being repelled is equal to the charged particle, which is, let me highlight it, the charged particle of this, right? The charge of this particle, times the electric field of Q1, which is this little sucker right here. Boom, of Q1. And thus, you have analyzed, understanding the electric field, you have analyzed, like, just by understanding the electric field, that if you include just the charge, you understand the force that is being acted upon this charged particle right here. And it applies to any other instances as you move other charged particles here or here, depending on the distance, not depending on the distance, depending on the charge, depending on the charge, you can continue analyzing what is the force that it is being experienced at that point due to the charge, the particle charge Q1. Okay, so another little known facts just for you to analyze, to think about. When it comes to positive charges, we always go outwards. Always go outwards when it comes to our field lines, our field electric lines, our electric field lines. Here we go. But when it comes to negative charges, the electric field lines are always going inward. So if you ever see in some type of exam a positive and a negative, and all of a sudden you see them connecting to each other, this makes sense. This makes sense because the field lines are going out of the positive charge and into the negative charge. It is showing an attraction. Okay? Showing an attraction. If there are two positive charges, then these electric field lines are going to be completely bent because they are being repelled. Okay? They're being repelled. So note to self, these vector lines never cross, or the electric field lines never cross. It has to do with understanding that an electric field line is only one type, one sign, and if they cross together, if they start crossing, then you have two different signs, and that's not physically possible. It's not in the physics realm where you have, you cross, let's say that you're really identifying, if they start crossing, it means that it is positive and negative. This particle right here, which is complete bull crap. Okay, so we understand this. I hope this was a decent explanation of the concepts, because I want to hit this problem, this baby right here. TP5-116, and this one is asking us, what is the electric field at the lower right hand corner of the square as shown below? So we are identifying, we want to analyze the electric field at this point right here. First of all, if you see this in the T, the first thing that you need to do is write the physics. It's like, that is the biggest hit. Electric field, all right, electric field it is. So you write down electric field is equal to Coulomb's constant times the charge of that particle over r squared. The charge of that particle over r squared. Again, in this example that I had here, it is the charge of the particle is the charge of Q1. And Q1 is right here. I wrote it, but I kind of like drew a line over it. So Q1. So that is the electric, that's how you get the electric field. So in this respect, it's either going to be, since there are three particles, it's going to be negative 2Q for the charge, Q, and Q. Okay? And r squared is the distance from the point, the charge, to the right-hand corner that we have to analyze. So we have to analyze from negative 2Q to P, let's just put it as P, to the right-hand corner, from Q to P, and from another Q right here to P. Those distances are going in r squared. Next thing that you need to do is that you need to make sure that you draw this. You understand how this works when it comes to drawing, because this will be either your savior or your doom. Okay? First of all, you treat this as you would for like the block 1 problems. We have to write a coordinate axis. So you go coordinate axis, And you identify that the positive x direction is on the right hand corner and the positive y direction is going upwards. Okay? So understanding for a positive charge, and you know what? I'm also going to do another thing. I will name the point that we're studying as point P. I will name this as E1. Not E1, actually. Let me just write it as charge 1. This I will name it as charge 2. And this I will name as charge 3. Okay? So just so I can have a reference on this. So, understanding that when it comes to positive charges, the vector line or the electric field line is always going outwards. So I am going to analyze that electric field line that is going straight into P. So since we have electric field lines coming out of Q1, but only one electric field line is going directly downwards into P. Boom. And it's this one right here that I highlighted, or that I put right here. I'm going to erase the other one so you don't get confused. There you go. This is the only electric field line that is going straight to P. We identify the first one. Now, let's identify Q3. Q3, just like the Q1, it is positive, so a lot of electric field lines are coming out of it, but there's only one that's going straight into P. And you're going to highlight that and put it in the direction of P because it's going outwards. Now for Q2 is a little bit different because remember what I said, when it comes to negative charges, the electric field lines are always going inwards. So you would write down a vector from P going away from P and into Q2. So you have set up all your vector components, and now the only thing that you need to do in order for you not to get as confused, I would just jump into a problem, but just in case, you can put all these together tail to tail. So starting at point P, I'm going to rewrite this. This is point P. Now, since this is point P, I am going to rewrite this Q1, since it's going downwards, going like this. And this is just to help you identify the direction of the electric fields in terms of your component or of your coordinate axis. So we have Q1, then Q2 has an angle, and then finally Q3 is completely horizontal in the x direction. In the x direction. Now, you can also do is solve for the angle. If you notice, this is an isosceles triangle because it has A's on both sides, equal parts. And that also means that if you break it in half, or actually this is a complete square too, that means that if you break it in half and make it a triangle, these angles right here will equal 45 degrees. So, in retrospect, the angle here, theta, is equal to 45 degrees. And you can rewrite your coordinate axis here at x and y. Boom. So now you're almost done, because now you have to treat this like everything that you treated in block 1. You have to solve for all the forces in the x direction, and you have to solve for the forces in the y direction. And solving for the forces in the x direction will get you the net force in the It's not even forces. It's not forces. I have to remember that. It is the electric field lines that we're solving for. And you would have to solve for the electric field lines in the x direction and electric field lines in the y direction. Because you can do that, the summation of that will give you the net electric fields in the x and an electric field in the y direction. So we can start off by saying x component, highlighting it, and saying, what are all the electric fields that are acting, electric field lines that are acting in the x direction in terms of P? So that means that we have Q3 that is acting completely in the x direction, and we can rewrite this as, and I'm going to write this as the sum of all electric fields in the x direction is equal to electric field of 3, and it's positive because it's going in the positive x direction, and then minus electric field of 2 because it is a vector component that is both in the x and the y direction. It has an angle. And because it has an angle, I also have to solve for it like this, cosine theta, to get the x component of it. So in order to get the x component, E2 cosine theta, and here to get the y component is E2 sine theta. And honestly, let me change this a little bit. Let me just erase this because it's kind of confusing, because this now becomes E2. This becomes E1, electric field of 1, and this becomes electric field of 3. So you can see that better. And E2 right here is the magnitude of E2. Now what you're doing is getting the y component of E2 and the x component of E2. So now what we do is apply the equation. K times, for 3 is just Q, over A squared, because it is the distance from Q, from the Q3 to P, minus the absolute value of 2Q, because now we're looking at Q2, over, and since this is an isosceles triangle, this also means that this is equal to A square root of 2. I would write A square root of 2 here to the power of 2 times K cosine of 45. This would equal to the square root of 2 over 2. And you can solve this and we'll give you a more concrete answer. But for now, let's just leave it as EX is equal, EX, electric field in the x direction, is equal to all this. Okay, and you would do the same for the electric field in the y direction. In the y direction, you would go as, the y direction is, the only thing that's acting is E1, electric field 1, but that one is going in the negative direction, so you have to identify as negative. Plus E2 sine theta, because the electric field is acting in the positive y direction. And you're using the trigonometric functions to get the y component of that E2 magnitude. Okay? And you would rewrite this as negative K, or columns constant, times charge, since this is 1, it's still charge 1, or just Q, over A squared plus K negative 2Q over A square root of 2 squared times sine of 45, and this will also equal the square root of 2 over 2. And I can just erase this. Oop. I can just erase this and write the square root of 2 over 2, because sine of 45 is the square root of 2 over 2, and the cosine of 45 is also the square root of 2 over 2. And I can solve now for the sum of all electric fields in the y direction. Understanding that I have the electric field in the x direction, the net electric field in the x direction, and the net electric field in the y direction, I can identify this, the electric field experienced at point P, which I named, is equal to the electric field in the x direction at point P plus the electric field in the y direction at point P. And this is the vector notation of it. So you basically, and that's for Philip. Philip, if you're listening to this, just remember, no, it does not equal to 1. Okay? The unit vector field, the unit vector notation is just like this. Now that you have this, now that you have the unit vector notation, it's asking you, and you can leave it like that, it doesn't ask for anything else. It's asking, what is the force on a charge Q placed at point P? So now, looking at the diagram here, we're going to add a charge here. Boom. But you already solved for the electric field that is being experienced at point P. So you can go back to your original equations where force is equal to the charge times the electric field at that location, experienced at that location, and you can go as force, this is point B, is equal to, the force is equal to Q, which is the charge, times electric field experienced at point P, in order for you, and let me just put the hat because this is a vector, in order for you to solve for the force. And you're done. Like, understanding, it's just basically a puzzle, right? You have all these equations and you just have to learn when and where to apply them. One last thing that I forgot, because I did write the equation, just make sure that when it's asking for the force too, just make sure that you write this equation as well. And I'm going to write it right here. The electrostatic force is equal to Q times the electric field. Make sure that, I moved it a little bit. Yep, it's very good. Done. So you have two equations that you need to use in order to get as many points as possible. We talked about the diagrams. Important to know the direction. So remember, positives are always going outwards. Positives are always going outwards. Negatives are always going inwards when it comes to electric fields. Okay, when it comes to electric fields, they're always going, like, positives are always going outwards, negatives are always going inwards for electric fields. Does not apply for actual electrostatic forces. You still have to identify the direction of the force when it's repelling and the direction of the force when it's attracting on a specific point charge. The point charge that the problem has identified. Okay, let me know if this video was helpful, especially for the quiz coming up on Wednesday. And if anything, I'll make some improvements on the video later on. This video not only helps you, it also helps me. I struggle a little bit with this subject, but I hope this helped clarify whatever issues that you might have had. And let me know if you have any further questions. You know that I'm here to help. That's part of the reason why I'm doing this video at 8:57 at night, guys. You're keeping me awake, away from my PlayStation 4 and Xbox. That is blasphemy. I need to get back on it. Anyway, always a pleasure. Have a good night.